Hey guys, so I just wanted to tell you that for this recording, I'm not gonna be here, but you guys always have to remember. Always keep that in mind. Bye, guys.
That's my son. Chandrasekhar had shown that the exclusion principle could not halt the collapse of a star more massive than the Chandrasekhar limit. But the problem of understanding what would happen to such a star according to general relativity was not solved until 1939 by a young American, Robert Oppenheimer. I think most of you know of Robert Oppenheimer under in a different context related to the Manhattan Project and so on and so forth. Nevertheless, let's continue. His result, however, suggested that there would be no observational consequences that could be detected by the telescopes of the day. Then the war intervened and Oppenheimer himself became closely involved in the atom bomb project. And after the war, the problem of gravitational collapse was largely forgotten as most scientists were then interested in what happens on the scale of the atom and its nucleus. In the 1960s, however, interest in the large-scale problems of astronomy and cosmology was revived by a great increase in the number and range of astronomical observations brought about by the application of modern technology. Oppenheimer's work was then rediscovered and extended by a number of people. The picture that we now have from Oppenheimer's work is as follows. The gravitational field of the star changes the path of light rays in space-time from what they would have been had the star not been present. The light cones which indicate the paths followed in space and time by the flashes of light emitted from their tips are bent slightly inwards near the surface of the star. This can be seen in the bending of light from distant stars that is observed during an eclipse of the sun. As the star contracts, the gravitational field at its surface gets stronger, and the light cones get bent inward more. This makes it more difficult for light from the star to escape, and the light appears dimmer and redder to an observer at a distance. I think it's all good to read a book like this, but this is fairly deep stuff, and I don't know how much just reading out a book like this will help, but I think you have to picturize something like a sphere being the star and the light that is emanating from the surface to be a whole bunch of rays over a solid angle of 2 pi, right, over a hemisphere. All these light rays that are going out in the hemisphere, they are being pulled back into the star itself because of gravitation. So you can imagine the light rays that are going flat along the surface of the hemisphere, situated at a point on the surface of the star, are being dragged back inside a lot more because they're horizontal, right? So they get dragged into closer to the surface. And those that are going vertically out are being maybe not really slowed down, because light rays can't be slowed down, but they may not be affected, but the ones that are at an angle are being pulled down. So the light rays are all getting closer and closer to the surface of the star, and the light rays that are supposedly going out horizontally are actually dragged back towards the surface. So I think that's kind of the picture I'm trying to make over here. I don't know how correct it is. Nevertheless, it's just a bit of an explanation for this passage. Eventually, when the star has shrunk to a certain critical radius, the gravitational field at the surface becomes so strong that the light cones are bent inwards so much that light can no longer escape. According to the theory of relativity, nothing can travel faster than light. Thus, if light cannot escape, neither can anything else. Everything is dragged back by the gravitational field, so one has a set of events, a region of space-time from which it is not possible to escape to reach a distant observer. This region is what we now call the black hole. Its boundary is called the event horizon. It coincides with the paths of the light rays that just failed to escape from the black hole. That's a good point. All the light rays that are trying to escape this structure, which is so strong in gravity, essentially imagine, I don't know, again, I'm trying to imagine various things. Imagine a fountain coming out of this thing. If the fountain is strong enough, you will actually see the water come out of the fountain. But if the pressure in the water pipe is not strong enough, the water is just going to reach the surface and then spread out on the surface. So instead of going in a three-dimensional stream out of the surface into a jet, it will simply spread on the surface. Same way, light over here, instead of streaming out of this event horizon, will spread along the event horizon. I have no clue whether this is the right explanation, but it seems good enough to think of it this way. Okay, so again, this region is now what we call the black hole. Its boundary is called the event horizon. It coincides with the paths of the light rays that just failed to escape from the black hole. In order to understand what you would see if you were watching a star collapse to form a black hole, one has to remember that in the theory of relativity, there is no absolute time. Each observer has his own measure of time. The time for someone on a star will be different from that for someone at a distance because of the gravitational field of the star. This effect has been measured in an experiment on Earth with clocks at top and bottom of a water tower. Suppose an intrepid astronaut on the surface of the collapsing star sent a signal every second, according to his watch, to a spaceship orbiting about the star. At some time on his watch, say 11 o'clock, the star would shrink below the critical radius at which the gravitational field became so strong that the signals would no longer reach the spaceship. His companions watching from the spaceship would find the intervals between successive signals from the astronaut getting longer and longer as 11 o'clock approached. However, the effect would be very small before 10:59:59. They would have to wait only very slightly more than a second between the astronaut's 10:59:58 signal and the one that he sent when his watch read 10:59:59. But they would have to wait forever for the 11 o'clock signal. The light waves emitted from the surface of the star between 10:59:59 and 11 o'clock by the astronaut's watch would be spread out over an infinite period of time as seen from the spaceship. The time interval between the arrival of successive waves at the spaceship would get longer and longer, and so the light from the star would appear redder and redder and fainter. Eventually, the star would be so dim that it could no longer be seen from the spaceship. All that would be left would be a black hole in space. The star would, however, continue to exert the same gravitational force on the spaceship. This is because the star is still visible to the spaceship, at least in principle. It is just that the light from the surface is so redshifted by the gravitational field of the star that it cannot be seen. That's interesting. This is redshifted that you cannot see it. It's become so low a frequency, I guess, or so long a time. Also, I'm thinking so faint, but maybe that's not necessarily true. However, the redshift does not affect the gravitational field of the star itself. Thus, the spaceship would continue to orbit the black hole.